Hi everyone. Konnichiwa, Ursula des. I am Ursula. I am a web developer, a creative coder, a math enthusiast, an occasional blogger. And these days you will find me experimenting with music visualization. For me, it's a way to play with the creative side of me. I usually work in a serious company, building serious stuff. And I like to balance things out, doing something more creative, something more playful. And I love coding. I love music. If I'm completely honest, I wish I were a musician, but I'm not. I tried, I'm not. And I found in music visualization a way to bring these two worlds together and just do fun things and expressive things in general. So what is music visualization really? To me, it's the art of turning sound into motion, into shape, into colors. So basically, it's making the invisible patterns in music visible. So let's see what this can look like. Okay. So yeah, today I'm gonna show you how you can build something like this. And for that, we're going to focus on two main concepts. They're quite simple, but very, very powerful for music visualization. And those are waves and the fast Fourier transform. And yes, we're going to make some visuals along the way, and we're going to see the code behind those visualizations as well. So the first thing is, sound is a wave. It can start from anything. It can be a guitar string, a vocal cord, a popping balloon, a propeller, like anything. When this object starts to move, it creates a movement that is back and forth in the air, so something like this. And those movements affect the air particles around it, making it go back and forth like a chain reaction. Now this animation is a bit simplified, but it should give you an idea how the sound travels through the air in a shape of a wave. And the waves have a few interesting characteristics that are going to be very useful for us, and those are the amplitude and the frequency. The amplitude determines how loud the sound is going to be, and the frequency measured in hertz is going to tell us how high the note is going to be. So higher frequencies, higher notes, higher amplitudes, louder sounds. So here we can see different notes. And they have different shapes, different waveforms. So let's hear it. Of course, in real life, the waves are not as simple like this. It's not like a simple sine wave. It can get very, very complicated. So let's see an example. What I'm doing here is playing different instruments and then all of them together at the same time. And you can see how each instrument has its own shape, its own wave, and then when they overlap, the figure gets a bit more complicated. So for example here, I'm taking a snapshot of the sound, how it looks at a specific moment, and it's really complex. We cannot really identify a pattern here. There's a lot of information and it's not easy for us to work with. So what we need to do is find a way to mix this complexity and turn it something into frequencies. That is what we can actually use to later map into different shapes, figures, and colors, and so on. So let's explore this a bit more. Here what we have is the wave in the time domain. So we can see how the amplitude changes. It could be like this, or it could be a bit more complex like this. And then again, we don't really know much about the sound at this point. We don't know what is the bass, what is the treble, what is the high mid. So we need to know where the frequencies are hidden behind this sound. We need to see the sound in a different way. And when we do that, we can have something like this. Here, this sound has a frequency of 5 kilohertz, maybe 5 and 10, 5, 10 and 20, and so on. And once we have this raw data, we can actually map it to the different shapes that we want to represent. And that is exactly what the fast Fourier transform does for us. It takes complex waveforms And it's going to break it down into its ingredients, showing us what are the frequencies that are part of the sound that we're listening at a specific moment of time. So to recap what we've seen so far, sound is a wave. It can have a very complex wave shape, and it changes over time. And the fast Fourier transform is the algorithm that is going to allow us to understand the sound, check its ingredients, and give it to us. So let's start exploring some code. I'm going to use P5.js for the examples from now on. P5.js is a library for creative coding that allows us to interact with sound, create shapes, and animate in general. So things our life easier. So what we do here is we're going to load the sound. We're going to pass the audio file that we want to work with. And then we're going to initialize the FFT object. I'm going to assign it to a global variable that we're going to use it later. And then in the draw function, we're going to call the FFT analyze function. And here is where we run the fast Fourier transform at a given moment. It's going to get the sound input as a data, and it's going to return an array with the information of the spectrum, the frequency ranges that goes from 0 to 255. And on each position of this array, we're going to have a number that is going to tell us how strong the frequency is at that given moment. And since the draw function runs 60 times per second, this data is constantly updated. So it's going to match whatever we're hearing in real time. So going back to the example here, I'm going to iterate over the array. And I'm going to say every element of this array is going to be assigned to the height. And then when I draw a rectangle, it's going to represent this height. So I'm going to draw everything inside the array from 0 to 255, and I'm going to draw how strong the frequency is at each point. So let's check it out. So the bars on the left represent the low frequencies, the bars on the right represent the high frequencies. And this is already music visualization. This already is what we can do. It's matching whatever it is that we're hearing. But in this talk, we're going to focus on something a bit more creative, something more playful. So let's see what else we can do with the fast Fourier transform. It has a method called getEnergy. So if we want to focus only on the bass of the song, we can call this method. It has other few keywords that you can explore, like the mid, the high mid, and so on. But if you want to focus on a specific range, then you can pass it as parameters as well, like this example. So now we have 4 different elements: the bass, the mid, the high mid, the treble. And we can use these values to map it to specific components in the canvas that we want to show. So some elements can react to the bass, some elements can react to the treble, and so on. And let's see an example of this. So what we're seeing here is some of the circles are responding to the bass, and the way they are affected is the line gets thicker as the frequency gets stronger as well. But you don't need to play with all the elements of a song. You can decide to play only with one thing, like the bass, for example. So what I'm doing here is drawing a curve that is called the Bézier curve. It's a flowing, smooth curve. And what I'm saying is, get the energy of the bass, and once it's on the strong side, and for me, and for this song, it means higher than 140, I'm going to generate the 4 coordinates that the Bézier function needs. And it's 4 coordinates because we have a starting point, an end point, and then 2 more points that define this pool that we were seeing. And that's it. P5 already provides the Bézier function. You don't need to worry about it or understand the maths behind it. But what I do want to focus on this example is in the method here called noise. And, sorry, this one, noise. So I want to stop here because I think noise is used a lot in creative coding. It's what allow us to have a very smooth and organic movement in general. So let me show you something that we're more familiar with, maybe, which is random. I'm showing this animation, which is some lines with some sine waves, and the waves are created with a random value. Notice how it jumps all over the place. It goes from one extreme to another. The values generated can be like 10 to 100 to 12 to 50 to 8. The jumps can be very high, it's all over the place, unpredictable, and it doesn't feel smooth. And yes, this could be valid for the animations that you're trying to create or the feeling that you're trying to generate. But sometimes we want something that is a bit more organic. And for that, we use the function noise, which is based on the Perlin noise algorithm. The way it works is we generate values that increment progressively. So each new value generated is based on the previous one, and that's why there's a relationship, and you can see them to be closer to each other. And this is the result. You have a more organic movement already. All right, so we've covered noise. So let's continue with some examples with FFT. What we have here is called a spherical Lissajous curve. It may look a bit more complicated. A lot is happening. It looks like a ribbon going around some sort of a sphere. And with P5, you can actually interact with the canvas. I can click and move it around. I can zoom out. I can zoom in. And the idea behind this algorithm, behind the Lissajous curve, is quite simple. We take a circle and we move it in 3 dimensions. I mean, don't ask me about the math behind it. That's way beyond me. But if we see the code or the formula behind this shape, it's just a few lines of code. So what we're doing here is going from 0 to 360, so all the way around the circle. And then we generate the x, y, and z based on the cosine and the sine functions. And this is what allows the motion to be smooth and repetitive. And then we multiply the angle with the frequency. In this case, I'm using the treble and the bass. And this is what is going to allow each axis to move at its own rhythm. And when those rhythms get together, the paths start to twist and weave together through the space, right? And it's the effect that we just saw. So the reason why I wanted to show you this is because sometimes some shapes look very complicated and the maths behind it are actually complicated. But if we find a way to find the formula behind it and start to play with it and the values, then we can already start to have amazing animations. All right, one more example for you. What I have here is circle rotating, and the music is affecting how strong the color it is. So it is responding to how strong the frequency is at a given moment. Let's explore the code behind this. First, we need to define the radius of the circle that we want to draw, and we're going to pass it to the ellipse function. And then we're going to define how many pieces do we want to draw around the line, around the circle, how many lines. So let's say I want to draw 4 or 8 or 32, it doesn't matter. We iterate through this amount of pieces, and the trick is here. We do a small rotation, and then we draw a line. Then we do a rotation again, and then we draw a line. And then again a rotation, a line, rotation, a line, as many times as we need until we cover all the pieces or until we go around the circle. And then when we use negative values in the line, then we can have lines facing the opposite direction. And you can start to see having different effects and play with it, right? So that's how we draw lines around a circle. So let's go back to the original animation. So what I do here is I'm getting the energy of the treble, and then I'm calling the draw function. And here is exactly what we saw. We draw an ellipse, and then I'm going to define the alpha of the color based on the treble, and I'm going to say map these values to something between 10 and 255. And this is going to give the intensity of the color, which I'm going to later set to the color object here. And from now on, every stroke is going to have this color. And the rest of the code is exactly what we saw. We define the amount of pieces. I go around pi and define how small the steps are going to be. So all the lines are pretty much close to each other. And then I rotate, draw a line, rotate, draw a line, and so on. So that's how you draw the lines around the circle. But if you want to have this rotation movement, what I do before drawing every line is have one small rotation. And so every time I call the draw function, it's going to start from a different position, right? And this offset is going to be increased in the draw function here. And that's it. That's all the code that we need to this. But of course, I think the fun part really begins when you start to interact with all the different frequencies in a song and different objects overlapping, interacting between each other. And it can look something like this, maybe. We've seen a bunch of examples with FFT. We've seen how we can map different colors, different shapes and motions using the frequencies. I think you're well equipped to start doing your own visualizations, but I wanted to show you something else, which is how we can take a different, any math formula and start to playing with it to create more interesting shapes. So I'm going to take the example of a sine wave. We've already seen the relationship between the sine wave and the sound, and I think this is a great way to keep visualizing the sound as it is. The formula is y equals sine of x, but this formula can get a bit more complex if we take other parameters into consideration. So we can have the phase, the period, and the amplitude. And the period, for example, determines we can stretch it, we can reduce it. The amplitude determines how tall the wave is. So we can play with this as well. And then the phase determines where we're starting to draw the circle from. So if we increase it or decrease it, we already have this movement from left to right, from right to left, right? So if we use these parameters and use the frequencies to affect these values, then we can have something like this. What I have here is a bunch of waves overlapping, constantly moving, so the phase is constantly changing, and the amplitude is affected by the frequency. And some of them are dotted, or some of them are filled, some of them have stripes. It's just playing a bit with different textures. And something else that I want to mention is color is also very important, and it's going to give a feeling, it's going to create an emotion as well with the animation. So don't feel afraid to experiment with different colors, see what fits better, what is it that you want to express, and yeah, just play with it. All right, one more thing about the waves is that they have this attribute that is called additive waves. So you can have two different waves. You can see A and B. They have slightly different formulas and they have different shapes. But when you combine them together, you can create new patterns, new shapes here that could be a bit more playful, maybe a bit more interesting. So if you use this property of the waves, we can have something like this. All right, those are all the examples I have for you. I think you are very well equipped to start playing with this. And the question is, where do I take this from, right? And that's what I want to show you next. There's something that is called an algorave, which is short for algorithmic rave. It's basically a performance where different artists and coders get together and they create both music and visuals live, right in front of you. So instead of bringing guitars or DJ sets on the set, they come with their laptops, they plug it in, and they project their screen so you can see whatever it is that they're typing. And you will see the music happening live right in front of your eyes. They use frameworks, there are different languages to do this. A lot of them are based in JavaScript. One is called Hydra to make the visuals, and Mercury to create the music. Let me show you how this looks like, actually. Hold on a second, click the wrong button. This one is Hydra for the visuals. And that one is Mercury. So they're both connected to the same server. So the input is the sound serves as an input in real time. So the animations can react in real time as well. It's pretty cool. There are a few groups and communities in Europe. I haven't seen many in Asia, to be honest, and I don't think there's one in Japan. So maybe you'll be the first to open one here, and who knows, maybe next time you'll be performing here in front of us. That would be pretty cool. All right. If you want to learn more about maths and what can be used for music visualizations to create something a bit more complex, I can highly, highly recommend all of these people. Let me fix this. There you go. They have YouTube channels. They have content that is very nice and easy to digest. It's very well explained, and they also show the code behind the math. So please check it out. I can highly recommend this. I hope that you try music visualization on your free time and have fun with it. You don't need to be a musician, you don't need to be a mathematician to start experimenting. Just open your code editor, play some tunes, and see what your code dance to. Arigato, Japan.